Okay, I guess we can start. So hi everyone, and welcome to our 9th lecture. And today we're going to talk about self-supervision. And so far, I guess we've been focusing in the course on supervised learning setup, where we have a large data set with ground truth labels, and we train a model to match those given labels. And I guess maybe you all wondered, how far can we go with this approach? Is this like the future of AI, or how far can we stretch supervised learning? Obviously, there are a number of problems with the supervised learning approach. First of all, it is not possible to label everything in the world. For some tasks, we cannot ask humans to give us like manual labels. For example, let's say I want to train a deep neural network to perform optical flow, right? We cannot give humans this task to provide us with, sub-pixel correspondences for every pixel between two images, or metric depth. Like we want to know the distance in meters for each pixel in a given image. It's not a task that we can give humans to manually label. Also, for some tasks, we just don't have enough label data. So labeling data, it's very expensive and tedious process, and scaling it up to, labeling millions and billions of images, it's very difficult and challenging. And lastly, there is this working assumptions that, if we build intelligent models, we wouldn't need massive amounts of label data. So if, for example, I present a baby this line drawing of a dog, they will be able to immediately recognize this as a dog, although they may have observed only natural dogs in the world, and they are able to generalize in one shot. But if you input this line drawing to a deep neural network that was trained on ImageNet, it will produce nonsense. I actually, the spider web is an actual result of an ImageNet model on a line drawings like this. So we humans have this common sense about the world from a very young age. We are able to kind of like generalize. We are able to understand intuitive physics and so on. And providing machines with this ability, with this common sense, is still like an open challenge. Some, well-known researchers like Jan LeCun treat common sense as kind of like the dark matter of intelligence. And again, we want to believe that if we are able to build better models that are closer to what we can do as humans, we wouldn't need to label everything in the world. So today, this is what we're going to talk about. We're going to talk about self-supervised learning, meaning that we want to learn with no human labels. Our supervisions are going to be derived automatically from our data in scale. And I like to think about kind of like self-supervised learning is divided into kind of like two subgroups. One group is direct self-supervised method. What I mean by that is that we have some task that we want to solve, and somehow we are able to get our labels, our supervisory signals completely automatically in scale without any human annotations. And the supervision signal is provided directly for the task that we want to solve. So some examples that you already seen is, GANs, like we want to generate images, and our kind of like labels or supervision is the data itself. You also seen this in homework 3 in ZSSR. Again, the supervision signal is provided to us by the data automatically. And I've been mostly working in this subfield in self-supervised methods. And I should say that, there is a large space of really being creative here and, applying advanced methodologies that we and skills that we have from computer vision and graphics to apply on data to basically extract supervision signals from data. And I hope I'll have time towards the end of the talk to give you an example. And the other group of supervised method are the indirect self-supervised method. And this is, you know, when you will read online the definition of self-supervised learning, this is probably what you're going to see. So here, you know, you have like unlabeled, possibly massive data collection. What we're going to do is we're going to define some pre-tasks, some proxy tasks that we want to solve. And this task is going to force the model to learn some semantic features. So we will train for this task. This task is not directly the task that we want in the end to solve, but it will allow us to learn meaningful features that are semantic. And then we're going to extract those features and then use them in order to improve a supervised task for which we may have like only small label data. And eventually we're going to evaluate the performance of this self-supervised method on the target supervised task. Okay. So for example, classification, where we have, you know, a small labeled data set. And now this proxy task, again, it has to be a task that will allow a model to learn semantic features that are going to be useful for the supervised task. So today we're going to focus on this setup. And this is, again, the common definition of self-supervised methods. We're going to look onto a variety of different proxy pretext tasks that, again, we can train without any human labels on a massive amount of data, you know, everything is done automatically. And we're going to show how this can allow us to improve over supervised tasks. And so we're going to cover a variety of different proxy tasks. Many of these works are coming from Alyosha's EFROS group. They have really done kind of like an inspiring line of works in this area. And we're going to start by talking about context as supervision. Guys, feel free to stop me if you have any questions. Okay, so using context as supervision is something that was already, when it arrived to the vision community, there was already evident that context can serve as a useful pretext task in text domain, in natural language processing. So in natural language processing, if you guys have heard the buzzword like word to vec, so the goal here is to learn an embedding for words that will be semantic and meaningful. So how do we do that? We extract a sentence or, you know, a part of a sentence, and now we want to train a deep neural network that will allow us, that will take in a word as input and will predict the context of this word, like other words in the vicinity of that input word. So the deep network has to kind of like, you know, associate this input word with other words in its context. And by learning to solve this task, this association task, the model after training is able to produce meaningful embedding for words that can detect synonyms and could suggest additional words for a partial sentence and so on. So basically the idea is, you know, how can we do this in the visual domain? So obviously, we cannot operate on single pixels, right? Because the single pixels doesn't have enough semantic information. It's a very low level piece of data that we have in an image, but what we can do is work on large patches. So for example, here in this work, the task is to predict relative patch position. So you have a patch A, and now I ask you, can you tell me where patch B go relative to patch A? Can you tell me?
Below.
Yes?
A should be on top of A and maybe on the left.
Yes, exactly. So basically, you know, out of these locations, if I want to ask like where should patch B goes relative to the blue patch, it should go to the bottom and the right. And the reason that we are able to do this is because we observed many different kind of like buses And we have prior knowledge about what a bus looks like, so we are able to do this. Like if a person never seen a bus in his life, it will be impossible to solve this task correctly. Again, like the intuition here is, let's train a deep neural network to solve this task. And now by solving this proxy task, we will force it to learn some semantics about objects. Okay. So this is the setup. We have an unlabeled image. We basically sample a random patch in this image, and then we look on kind of like 8 possible locations relative to this blue patch. And we sample another random location within those 8 possible patches. And now we want to take these 2 patches and feed them into a CNN. And the job of this CNN is to predict, where does the red patch is coming from relative to the blue patch. And we can formulate this as a classification task. So we assign a label to each one of those 8 positions, okay? And now the task is, a multi-classification task. We want the network for this input to produce index 3, right? And this CNN here, it is illustrated as 2 different CNNs, but this is just kind of like for illustrative setup to stress that you feed in each patch individually in a separate forward pass. And but this CNN are basically the same CNN. They share the same weights. Okay. And now after we train this thing, what we can do is we can extract this patch embedding. This CNN, after it is trained and we solve this classification task, it provides us with a patch embedding. We can extract the last fully connected layer from this model and look on kind of like, and now this feature activation at the last layer serves as a patch embedding, okay? And now maybe, some of you that can take a close look, you can see that the patches here, they have gaps between them. And also they are not perfectly aligned. So these are not kind of like an image grid patches. And the reason for that is because if we don't do that and we naively kind of like look on, adjacent patches that are kind of like a regular grid, there are some low-level cues like, boundary of patterns and texture, like textures that continues across patches, that these are kind of like signals that the network could potentially use as a shortcut. It could just look on some low-level information like an edge and solve this task. So in order to prevent the network from doing that, it is important and to introduce kind of like gaps between those patches and to jitter them. And so I guess in many cases, we're gonna have to avoid this network cheat and avoid trivial solutions and reason about them. And I'll talk about it throughout the entire talk, okay? So after doing this jitterness and gaps between the patches, we kind of like prevent the network from learning these simple edges or texture continuity. And then even after doing that, what the authors observed is that, for some images, the network is doing a really amazing job at locating these 2 patches. So how can that be? These patches are super similar and we cannot, reason about their relative location. So why the network succeed in solving these tasks? This is kind of like very suspicious. So I guess first takeaway message, always be suspicious of your network and never fully trust it. So they looked more closely into this phenomena and tried to understand, what's going on here. And it turns out that what's happening is, so first of all, in order to test this, they did the following toy test. So they basically took an image, extracted the patches, and now they trained a CNN to predict, to take in a patch and predict its absolute location in the image, like X, Y coordinate, okay? And they observed that for some images, the network is able to solve this task quite well. And again, why would the network be able to succeed in this task, right? And then it turns out that the images that for which that they were able to detect XY location, they were affected by this phenomena that is called chromatic aberration. And this is a phenomena where the lenses bend in a way that kind of like they reflect different wavelength, a different amount. So what I'm visualizing here, so this is like an ideal lens where all the colors are kind of like all the wavelengths are intersecting, projected onto the same location. And this is how an image with this ideal lens would look like. But under kind of like chromatic aberration, this is what you get, okay? So each kind of like wavelength is projected by a different amount, and then you will end up with these kind of like shifted wavelength images, shifted colors in the image space. And the network could actually, pick up this low-level signal and use it to solve this task, okay? So how can we solve this? Basically, what they did is to randomly drop 2 out of the 3 color channels in the image, and basically discarding the color information randomly to prevent this from happening. So I guess, again, like networks are lazy. If there are low-level signals that they can pick up to solve this task, they might do it in many cases. And you will notice that if you take a look at all these papers in the self-supervised world, typically you have like a section which is like avoiding trivial solutions, coming up, identifying, shortcuts and so on. So this is, although these tasks may look very kind of like intuitive and straightforward, in many cases, it's not trivial to actually train for those tasks. Okay?
Can I have a question?
Yeah.
Is it not specifically about this, but is it relevant also for the patches in visual transformers that the network might learn, like in the embedding and the way the attention, like the interactions between patches can be affected by like non-semantic things?
Again, I don't think it's something that necessarily has to be tied to an architecture. It's the fact that it's more related to your data, training data, and tasks. Okay.
But considering that the way the input for the visual transformer is by non-developing core patches,
Yes.
so like I wonder if it might cause like the optimization process or the training process to be a bit more challenging, since the embedding can be affected by very low-level cues and not like interesting semantic embeddings.
I see. I don't know if there are, it could be, I can see your intuition. There are some line of works that are trying to solve like, that are applying self-supervision in the transformer setup. So I encourage you to look more closely on that. My intuition is that it's less kind of like affected by the architecture here. Here, there is kind of like an inherent problem in your problem setup, okay? You are presenting it with some data and you are presenting it with some tasks that you want to solve. And, other than that, you are not guiding the network to do anything. So it can pick up any signal that is relevant in order to solve this task. And it's not necessarily the signal that you would like the network to pick up in order to give you what you want. So it could be low-level cues, and but you want the network to look on semantics, okay? So again, I think it's more of a task data problem than an architecture one. All right, so let's see some results. So the first thing they can do is, again, as we've seen in visualizing and understanding lecture, we can do nearest neighbor. So we pass in patches, we extract like feature embedding from the last fully connected layer, and now we can retrieve nearest neighbors. And you can see that it's really nice here that we get semantically meaningful similarity between patches, although the network has never observed any semantic labels, just by solving this relative patch task. And this is what you get with the random initialization of the network. So before the network trains, you can see that the nearest neighbors are not that meaningful. And these are the nearest neighbors that you will get if you train a neural network in a supervised manner using the ImageNet labels. And again, at least from a nearest neighbor perspective, it looks very much kind of like more similar to the nearest neighbor that you will get in a supervised manner. So this is a proof of concept that there is semantic information embedded in those embeddings. And now how can we utilize this to do, to perform transfer learning, right? So now we are giving, our goal is to, let's say, solve some classification task for Pascal VOC dataset, which is a small dataset that we don't have like, many labels. And what we can do, we can take our pretext task, train it on ImageNet in a self-supervised manner without labels, but it's a massive data set, much larger than the Pascal one. And then after we've done this, we're gonna, there are two options, common options. One is that you keep the CNN part fixed, and now you only train the fully connected layers for the given classification task. Or the other option is that you train, you initialize the model using the self-supervised network weights, and now you fine-tune the entire thing for the given classification tasks. And you do this.
Which is better?
What?
Which of the method is better?
I mean, the first one, when you freeze this one and you only train the fully connected, is more constrained. You are not allowing the features here to change at all. So in a sense, if you could, match, if you can get very high accuracy using this setup, it kind of like demonstrate more that the learned features are very powerful. So I guess in those papers you will often see the two setups, and now we can take a look also on the numbers for classification, detection, and segmentation on Pascal VOC. So what we can see here is the accuracies if you do the pre-training in a supervised manner on ImageNet. So we take a model that was trained on ImageNet labels on the full training data set, and now we fine-tune it or only train the fully connected layers for the small classification tasks. So this is kind of like the gold standard. This is where we want all the self-supervised methods to reach in the end. And this is the accuracies when there is no pre-training. You just take the model and you directly, you randomly initialize it and train it on Pascal VOC. And here what you can see is the pre-training with relative patch locations, and you can see the improvement over, a significant improvement over the random initialized method. Okay, so we can generalize this task of predicting relative patch locations, and now we can consider, the following task. We want to solve a jigsaw puzzle task. So we take a grid of 9 images, we scramble them in some random permutation, and now we want to, the task is to solve the puzzle. We want to reorder those scrambled patches into their correct layout. And maybe you can already guess that the problem with this kind of like task is that the solution space is huge. You get like for 9 tiles, you get like 9 factorial possible permutations. We cannot train a network on such a huge solution space. So what we have to do here is to kind of like consider only a subset of permutation sets, and I'll talk about it later. But let's kind of like see the setup. So here what we have 9 tiles. They are shuffled by random ordering, which we take from kind of like a predefined set of permutations. And now for each permutations, we can assign an index label, okay? So let's say this permutation is given with index 64. We take the 9 tiles, we again randomly order them, and then we feed each patch, again, very similar to what we've seen before, into kind of like a CNN network. And then we have some fully connected layers, and the output is the index of the ground truth, the predicted kind of like permutation index. And again, this is kind of like formulated as a multi-class task, multi-classification task, and we can use cross entropy with respect to the ground truth permutation index in order to solve this. And again, you can see here, we illustrate this as kind of like different networks, but they are all sharing weights. So this is essentially just the same neural network, and each time we fit in each patch individually into the network. Yes?
So this is the task of training only on the 100 permutations of all of the set, right? Because the softmax, I see the last softmax layer has only 100 elements, so it's...
Yes, so this brings me into the next slide. As I said, like 9 factorial possible solutions is too big, and we need to select the permutation set. So there are 2 factors that needs to be brought into our attention when we select the permutation set. First of all, the size of the permutation set and the distance between permutations. So for example, if we take these 2 possible permutations, the only difference between them are in these 2 patches, which are kind of like very similar to one another. And it will be very difficult for a network to get the correct answer here, because these 2 patches are so similar, and the only difference between these 2 permutations are in these 2 patches. So this makes the problem much more ambiguous. So they did some ablation study, very briefly to go over their results. So what we can see here is kind of like here, they changed the number of the permutation set size. And here you can see kind of like they measured the distance between possible permutations in these 2, 3. And what we can see here is as follows: like smaller permutation set leads to higher accuracy in the task of solving this Jigsaw puzzle. And that makes sense. Like you only need, the network task is easier. But also what we can see here is that the smaller permutation set also leads to lower detection performance, like 49.7 versus 53.2. So it means that, you know, by making the task easier, the network doesn't learn as meaningful patch embeddings as with the large permutation set. So we make the problem more challenging, but it actually helps the network kind of like learn more semantic and meaningful embeddings. Also, what we can see here, so here the number of permutation is fixed, and they only change the distance between the possible permutations. So what we can see here is that larger distance between permutation leads to higher accuracy, okay? Higher accuracy, and it also correlates with the detection, the performance on detection, okay? So this is kind of like, you know, ablation that they did, which I think is nice because it allows them to kind of like select the permutation set in a sensible way. Okay, another type of image content or context that we can use for supervision is, you know, we can solve this problem of image inpainting. So what we do here is we mask out a region from an original image, and we want to train a deep neural network to predict it. Okay, sounds very straightforward, right? We can obtain, again, as much training data as we want. All we have to do, we have kind of like an image with a mask, and then we train this deep neural network that has encoder-decoder type of an architecture to produce this missing region. And all we have to do is establish a loss between the ground truth patch and in the missing region and the predicted one. So I guess the most straightforward loss that we can apply here is a reconstruction loss, right? Like we can just say L2 distance between ground truth and predicted content in that region. What do you think would be the problem with this approach?
Blurry.
Well,
blurry.
Why would it be blurry?
Because the average will be more important than the details.
Yes, I mean, you could have different images that might have very similar context, but will have different region, will have different solutions in these masked regions. So we might have like a multi-model distribution of possible patches in this region, but when we are kind of like applying this L2 loss, we are solving for a unimodal solution to this task. So it will be kind of like an average of all possible solutions of this patch, given the context, okay? So what they did here is they added the adversarial loss, which you guys seen previous lecture. So in fact, what they want to ensure here is that, you know, the adversarial loss will ensure a realism. So they want this patch to look realistic with respect to other patches in the data set. So I'm not illustrating it, but there is an additional discriminator here that looks on the predicted content and tries to determine or discriminate whether this patch is realistic or not. Okay, so this adversarial loss, in the sense, allow us to pick a mode in this multimodal distribution of possible solutions. So again, let's see this effect. We have the reconstruction loss that allows us to kind of like ensure the global structure, correct global structure in this region, but it will be very blurry because it is an average over all possible solutions. And when we add like an adversarial loss, this is the result you can get. And more formally, we define the reconstruction loss as an L2 loss. So F is our deep neural network that takes in a masked input image. M is the mask, it equals 1 in the masked regions and 0 elsewhere. And we apply the reconstruction loss only in the masked region.
The adversarial takes into account only the specific crop or the entire image.
So here the reconstruction, you can see that it's a multiplication. It predicts the entire image, but the reconstruction loss is applied only on the masked region. You can see it by this multiplication here.
No, I mean the adversarial loss.
So in the adversarial loss, this is the setup. Again, it's a bit kind of like messy. If you look in their paper, they have several setups, but their general setup is that you kind of like look on the entire image, and the discriminator is trying to discriminate the entire image, whether it's real or fake. And I think the reason it's a bit messy in their setup is, again, because we have to deal with the network cheating, and they had to kind of like experiments with all types of different types of masks, because if you only work with this rectangular masks, again, the network could pick up low-level cues. It could identify corners, it could identify, on which side you are, and so on. So they wanted to work with more general and more challenging masks. And if you work with this mask, you can no longer, input only the masked regions into a deep neural network. So again, you will see a section that exactly talks about that in the paper. And these are the types of results that they could get. And you can see that, it's not something you would like to use in Photoshop, right? The quality here of the filling is not great. But again, the goal here is more than kind of like solving this inpainting task, is to learn meaningful features. And if we repeat this Pascal VOC setup where we want to, fine tune on detection and classification tasks using the learned features, you can see here that, relative patch location, the context encoder, and the Jigsaw puzzles, they are kind of like improving over what we had in the random initialization setup, and they are able to kind of like learn meaningful features that could benefit supervised tasks. And what else can we see here is that the Jigsaw puzzle performance is the highest. And I guess a nice takeaway message from the paper is that a good self-supervised task is neither simple or ambiguous. I guess the Jigsaw puzzle pass to me, it is the most challenging task out of those 3 tasks. And it's apparent that the learned model has more semantic information embedded into it. Okay. Any questions so far? Okay. So going back to our kind of like slide of all possible different types of proxy tasks that we can solve, I'd like us to also take a brief look into these two categories. Okay, and I'll start by this task of predicting image rotations. So it's kind of like very, again, simple and straightforward. We're gonna take an image, we're gonna rotate it randomly in some rotation, and now we wanna train a network to predict the rotation that was applied on the original image. And again, we as humans, we can kind of like know and predict what was the rotation because we have semantic information, we have prior knowledge about objects, about concepts of objects, about their regular layout in the world, and we can solve this task. So now we want to also train a deep neural network to do that, and hopefully it will also learn concepts about objects and semantics. So our training data are basically images rotated by 4 different degrees. And again, they chose these kind of like 90, 180, and 270 rotations because they can implement this with flip and transpose operation, avoiding the need to apply any interpolation to do that. And the reason to avoid interpolation is because we don't want to introduce any low-level signals to the network to pick up. Okay. And now, again, we can formulate this here too as a classification task. The classes are the applied rotations. We have a 4-way classification task. So here you can see the input image. We apply a random, all these four different kind of like rotations on that input image. It goes into a ConvNet model, which again shares weights here. It's the same model. And we're gonna predict the label that we assign to each rotation. Okay, so again, we can use a cross entropy loss with respect to the ground truth and solve this task. Okay, and a nice thing that they showed in their paper is they looked on the salient parts image regions that the model looks at. So what you can see here on the left, these basically, they basically call it attention maps. The way that this is computed is by taking the magnitude of activations at a given conv layer and scaling it up by some factor. So you can see here these attention maps for a supervised model that was trained on ImageNet. So you can see that it highlights semantic regions in the image. And here you can see as a comparison, the attention map that was produced by the model that was only trained to predict rotations, okay? So it's quite comparable, and you can see that it highlights also kind of like semantic regions in those images. And another nice thing that they showed you, they visualized the kernels that are learned in the first layer under a supervised model trained on ImageNet and under the self-supervised model using rotations. And you can see, first of all, that both model learns these oriented edges and color patterns as we've seen in lecture 4. And now what you can also see that the variety of learned features in the self-supervised setup is even larger. So it learned like a better, a richer type of representations of the images in the self-supervised setup than the supervised one, which is quite remarkable. Okay, let's take a look briefly on also colorization tasks. So here the task is as follows: we take grayscale image, we take images, we remove color information, and now we want to, the task is to generate a plausible color image from a grayscale image. So these are kind of like examples of, some training data examples. We have the grayscale and we have the ground truth color image. We can produce as much training data as we want, okay? And the task now is to train a deep neural network to take this grayscale image and produce the color information. So in more details, and they decided to work in LAB color space, which corresponds better to kind of like human perceptions of colors. So the L channel kind of like represents lightness. This is the lightness channel, and this is what the network takes as input. And now the output are the two other kind of like AB color channels. And again, this seems very straightforward, but one problem here is that in terms of training loss, again, if we only kind of like solve this as a regression problem with L2 loss on with respect to the ground truth is not sufficient. You could have many different types of fish that may look very similar, but will have different colors. And if we will just, apply L2 loss, we will kind of like converge into a mean fish color. So instead, what they did is they took the AB color space, they discretized it, and now they define the color of at a given location as a distribution of colors in this discretized space, and they can again formulate this as a multi classification task. So what you can see here is again the cross entropy loss over color distribution. Now, the ground truth color, you may think, is just a one hot vector in this space, right? Like I have, let's say, blue. So it will be kind of like, I can, if I assigned an index to each one of those bins, I can represent the target color in using this one hot vector. But in practice, because this is a discretized space, what they did is for each kind of like ground truth color, they find like 5 nearest neighbors, and they weight the ground truth color according to those 5, the similarity to those 5 nearest neighbors. So they can actually define kind of like a soft or a soft hot vector, or a distribution of the ground truth colors, and not like just one hot vector. And you can see here again the effect of those training losses. If we train just using L2 regression, we get all these kind of like average grayish colors, and with the multi-model class loss, we can get this result here. Questions? Okay.
Why is the bird is blue?
What?
Why is the bird is blue?
What is? Sorry, I cannot hear you.
Why is the bird is blue?
Why the bird is blue? This is, I guess, was one of the kind of like modes in the distributions of colors in birds in those in the training data. So it converged into kind of like one mode of the distribution, but at least we didn't get kind of like these all averagey gray colors.
But there is no adversarial loss in this case.
There is no adversarial loss. There is no adversarial loss. You obtain this here by modeling, instead of like doing L2 regression, by modeling color distribution, and not kind of like a unique solution, unimodel distribution of your ground truth data.
Just from this picture, we don't know that it necessarily kind of collapsed to one mode. Maybe they just visualize like, one mode of the distribution.
It could be, that's true. I mean, it's a bit like that because the ground truth training data is a unimodal distribution, because for each example, you give a pick only at a single point. They haven't demonstrated if you could sample, I think, at least I haven't seen it, they haven't demonstrated you can sample different types of outputs for the same input. But it could be that you will get like, I don't know, multimodal distribution. And here you can see again the numbers. So again, the supervised pre-training on ImageNet, the randomly initialized model on Pascal BOC, and the rotations that kind of like beats all the other previous self-supervision method that we've seen. Here you can see colorization. This is another method that we didn't have time to cover, that also from the same group by the same authors, that also performs a colorization task. So with that, I think we're going to take a break, and let's see, what time is it? It's 10. So we will be back here at 10 after 10. Okay?
May I
Okay, so we are back. So I guess so far what we've seen in the lecture so far is that, you know, we can define these proxy tasks, but and then we train a model for solving a specific proxy task. But as someone pointed earlier, the question is, can we define a more general pretext task, or can we unify all these tasks into kind of like one model that, you know, will have them all? And so basically what we want to have is a model which is not specific for a given task and can represent like a set of possible tasks, and be much more general. And what we're going to talk about is a very recent method from 2018. It's called SimCLR, a simple framework for contrastive learning of representations. Notice that it already has like over 12K citations. It's a highly cited paper and created a lot of buzz, mostly because of this result. What we can see here is that, you know, if we train a feature encoder on ImageNet using SimCLR, like in the same manner that we've done so far, and now we freeze that feature encoder, we don't fine tune it. We only train kind of like a linear classifier on top of this feature encoder with labeled data. We can kind of like beat or achieve state-of-the-art self-supervision results on ImageNet. What you can see here is ImageNet top 1 accuracy. And you can see that it's kind of like suppressing a supervised ResNet 50 model on ImageNet. So this is quite remarkable. And now we're going to talk about, you know, in detail what they did here. Okay, so again, we want to have we want to have an image, and now the goal is, you know, to have kind of like a general set of possible kind of like proxy tasks that the network should solve. So we can define a set of augmentations that are applied on the original image. Those augmentations can include, you know, cropping. They can include color distortions. They can include kind of like the inpainting setup, where we kind of like cut out a certain region in the image, adding noise, doing some filtering, rotations, you know, a really kind of like a varied and large set of augmentations. And what we want is basically that the model will know that this original sample reference image X is the same object as those images, right? These are kind of like referred to as positive examples. The network should kind of like learn an embedding that will kind of like put this, the embedding of this original image close to the embeddings of these positive examples. On the other hand, we want to also teach it what is not the same object examples. And for that, we're going to introduce the model with a random set of other images. These are going to be kind of like our negative examples. And these are not the same objects. So we want to teach the model that these are the same and these are not the same. Okay?
Can these objects be from the same class as the original image? So if it will be another picture of a dog, we still want the embeddings to be different, right?
Yes, yes. So it's just a random set of other images. And I'll talk in more details about how we construct our training data, okay? And again, keep in mind that you're not using any labels. So you don't know if it's another dog or not. And you cannot use this during training. So what we have here is, again, an encoder, F. And we're gonna input some original image X. We're gonna extract some learned features from that reference image X. And we're gonna do the same for the positive and negative examples and produce an embedding for those as well. And what we want to have is some kind of, given some chosen score function, we want this encoder to produce an embedding that will place the positive example much higher than the negative example. That will give a score of similarity between our reference and positive example, a higher score than our reference and a negative example. Okay. And so let's see how we kind of like construct this using mini batches. So first of all, we sample a mini batch of images from, let's say, from ImageNet. So this is what you see here, a random set of images. And now we're gonna randomly pick 2 random augmentations from a set of predefined possible augmentations. And we're gonna apply these 2 augmentations on all the images. So if we had n images here, we're gonna have 2n images here after augmentations. And now for each example, X, we're gonna define the positive example as the same kind of like image after applying a different augmentation to it. And the rest of the augmented images in that mini batch as our negative examples. So we have 2n minus 2 negative examples, and we have 1 positive example for each kind of like image in the mini batch. So again, this is a setup. We have an original image, a positive example, and a set of negative examples. And now we need to define a loss, okay? And this is the definition of the loss. So what we can see here is that in blue, I mark kind of like the score for the positive positive pair. And in red, I mark the scores for all the negative pairs. And my question to you, does this remind you anything? Like what we can see here inside those brackets. Does it ring a bell? Have you seen this type of a loss before?
Softmax.
Exactly. So this is a softmax cross entropy loss for an n-way softmax classifier. And here the classes are kind of like the positive and negative examples, right? So basically what the task of contrastive prediction here is to identify for a given sample X, we want to be able to identify or classify the positive pairing example out of this set of 2n minus 2 negative examples, okay? And of course, we do this kind of like we take the expectation of on all possible reference images X.
Ali?
Yes?
Does this loss compensate for the imbalance here? I mean, we have 1 positive example and...
So it actually turns out, again, so that brings me kind of like to this slide. This loss is not new. This loss is is very known in this area of contrastive learning, where the goal is to kind of like group similar examples together. And it was already kind of like originated in previous work. It is also known as kind of like noise contrastive estimation loss, info NSE loss, contrastive cross entropy loss, and so on. And it actually has some nice theoretical derivation as well that, again, we won't be able to cover here, but there are lower bounds for this loss using the mutual information between Z and ZI plus the similarity, kind of like the mutual information between our embedding and the embedding of the positive examples. And also, there are results that have shown that you need a large number of negative. It is required to have a large set of negative examples to obtain good representations. And it is also validated empirically. So that's the setup that they also wanted to work with here. They wanted to have like a large set of negative example and a single positive example. Okay.
Ali?
Yes?
There is also something I know from different papers called triplet loss.
Yes, it is also related to triplet loss, but triplet loss is only looking at triplets. Here we are looking at a larger set of negative examples. So in triplet loss, you are trying to kind of like bring close the positive example and push back the negative example, but you have only kind of like one positive and one negative. Here is kind of like you have a large set of negative example and a single positive example, but it's definitely related. Okay, and the similarity is typically the similarity within the exponent here is typically taken as the cosine similarity between the features. Okay. So I want to go over kind of like a pseudocode of this framework. Again, what we do, we sample an n-size mini batch, and then for each sample, what we do here, and we apply two different types of augmentations. We then compute a latent representation by feeding it into an encoder. And actually what they did here is not applying the contrastive loss directly on those embeddings H, but actually kind of like projecting it using another kind of like projection head G to produce those Zi and Zj, and then apply the contrastive loss on those projected embeddings. So our positive examples are Zi and Zj originated from the same original image, and the negative examples are all the other 2n-2 augmented images in the batch, and we apply the NSE loss for all the positive pairs in our mini batch, and we back propagate gradients through both G and F. And then after we train this, we basically throw away this projection head G and use the embeddings that are outputted from F. And let's see, again, what's a little bit of the intuition about this projection head. So basically what they showed is that by applying this contrastive loss, we may kind of like throw or discard useful information that we need to have for downstream tasks. So they kind of like project this embedding and by applying the contrastive loss on the output of the projection head, they kind of like allow this encoder F to still kind of like preserve some information that may be discarded when we are applying the contrastive loss. Because think about it, the contrastive loss is trying to make the model to be invariant and robust to all these different transformations that we applied on our training data. So what they show here is that the projection head improves the learned representation for downstream tasks. This is the performance if you don't have any projection head and you apply the contrastive learn loss directly on those H embeddings. And in blue and brown colors, you can see the performance with linear and non-linear projection head here. So we can definitely see a boost in performance.
Tali?
Yes?
About this projection head. So this G just removes some information, and this allows us to still have a good embedding at the HJ, right? But I don't understand actually the G. Why do we need G?
Okay, so I guess again, what is the task that we are trying to solve here? We are applying a whole set of augmentation to a given image, and we tell the network, ignore these augmentations. This image is the same as all these augmented images. So in a sense, we are telling the network, discard, be robust or be invariant to all these different transformations that we applied on the input image. At least so the network has to discard information. It has to be kind of like come up with a representation that will allow it to, for example, if I applied lots of color augmentations on my input image, my representation wouldn't, ideally wouldn't contain any color information, right? Because it has to be robust to it or invariant to it. But this color information might be useful for some downstream tasks. So we might want to still preserve it, okay? So I guess what they did with this projection head is just kind of like delay the discussion of information into kind of like the output of G, and then obtain this, and then after training, you kind of like discard this G and take the feature representation from an earlier stage of this representation that empirically showed that you can preserve more information that is useful for the downstream tasks.
So this is basically the same as having a representation from the intermediate layer.
Exactly.
your network.
It's the same. Like think about it like you have another layer and now you apply the loss on the final output, but then your feature representation is taken from the layer before. So it's basically the same. Okay. Okay.
So the intuition here is that the last layer is like trying to be best on the task that it's training on. So we want maybe a previous layer that is not as fitted to this task, this proxy task.
Yes, I mean, you can think about it again. We've seen this in the class before. Like, for example, when we talked about feature visualization and so on, we had like two fully connected layers and one that produced like the final logistic kind of like the probability distribution over possible classes. And we looked on a layer that was before that because in the very end, all the images of a dog will collapse to the same one-hot vector, ideally, of 1 in the dog class and 0 elsewhere. And we discarded so much information. So instead of looking at that final output, we are looking at the layer before that that still must learn semantic information that is, can be reduced to give us this final output, but it contains more information. So it's exactly the same intuition here. Okay. Okay, another kind of like, as I mentioned, this framework is required to work with large batch size. And what I mean by batch size, it could be like, I don't know, 8,000 size of a batch. And that requires kind of like large memory, required working with TPUs. And it's really hard, like it's not something we can train here at Weizmann, for example. And there are solutions to this. So for example, this work, the momentum contrast for unsupervised visual representation learning, or MOCO, they decouple the batch size from the number of negative examples by having and storing negative example in a running queue. Again, I'm not going to cover this work here, but this is kind of like just to get you familiar with this problem of this requirement of large batch sizes, and be aware that there are more advanced ways of kind of like handling the negative and positive examples here. And now I want to show you another work from Alyosha's group that is using contrastive learning, but for a completely different task, to do unpaired image-to-image translation. I guess you've seen this in our generative model lecture before, but the task is as follows. You are given a training set. You have like a set of images of 2 domains. And now you don't have any correspondences between images of horses and zebras. And the task is, given an image of a zebra, or it looks more like a donkey here, but produce an image of a zebra that contains the structure, the pose of the original image, but will transfer correctly, the appearance of a zebra. People have tackled this problem using GANs and the cycle GAN and so on. Here they took a different route, and I think it's a very nice kind of like use of contrastive learning here. So as previous work, they still have a discriminator that look on the output image and kind of like tries to determine whether this image is realistic, is a real zebra image or a fake one. Okay, by introducing it examples, the real examples are coming from our data set of zebras, and the fake examples are the output of this generator. And now the intuition here is that if what we want from this model, we want that the different object parts under the translation are basically the same, right? Like we want this model to learn an embedding that will say that a head of a horse is the same as a head of a zebra. However, legs of the horse should be kind of like differentiated from other body parts of the horse. And they formulate this as a contrastive learning task, where basically they're saying, again, these 2 patches has to this generator has to learn an embedding, which will place these 2 patches nearby in the embedding space. But if we sample different patches within the same image, they should be kind of like placed far away from this head patch here in the embedding space. And again, we can formulate this as using the same loss that we've seen so far. These are the notations for the learned embeddings for a given reference patch in the output. A positive example would be the corresponding patch in the original image, and a set of negative examples will be random patches within the same images. And we want that the corresponding patches should have high similarity, okay? So how do we do? Yes, how do we do that exactly? So we take our cosine similarity between our reference patch and the positive patch. We want it to be high. And we want the cosine similarity between the reference patch and all the other negative examples, which are random patches within the original image, to be low. And again, we can form this as using the same formulation that we've seen. We can apply a softmax on these similarities and formulate this as kind of like a multi-classification task. Using the same info NSE loss and SimCLR loss. The main difference here is that, in SimCLR, we had handcrafted data augmentations that was used to produce our positive and negative examples. And here, the positive and negative examples are the input and synthesized images. Any questions?
So here, the generator is encouraged to produce zebras only by the discriminator, right?
And this loss, yes, like the real.
This loss, if you didn't have the discriminator, you would just want to output the same image. That you don't know that you want to output a zebra.
Yes.
Yeah, okay.
Yes.
I have a question. How do I know the location of the head in both of the images?
They are aligned. Like, you look at these two images, okay? So they are basically aligned. Like this horse, this output zebra should ideally have the same pose, the same structure as this horse image, but only differ in kind of like the.
Yes, but in the beginning, when I just started to train, I will not get any alignments. I will not get any zebra in the end. In the beginning.
You're talking about the beginning of the training?
Yes.
I mean, it takes some time for the network to converge. I'm not sure if they had like any way of dealing it differently in the beginning of the training. But overall, the two images are aligned. And because they are aligned, you can apply this loss. So this will kind of like ensure, this will encourage, the structure, right? Because you are basically saying to this generator, these two patches should have the same representation. So it actually encourages some identity in some space. And I imagine that in the beginning of the training, you will see something kind of like blurry and not having stripes of a zebra, but that overall kind of like have the same structure of it. And then when the adversarial loss is kicking in and starting to learn meaningful features, you will start to see kind of like the zebra stripes and patterns on top of it. Okay, and so here you can see some results, and they compare this to CycleGAN, and they show that they're able to learn better kind of like placement of textures. And also what was nice about this is that they could also work in this setup where they didn't have a lot of training data. So they can work also even on a single image as a training example. And I guess another nice visualization that they did in this paper is visualizing the learned similarities. So what you can see here is a blue point here. It's a bit small, but I hope you can see, and a red point here. And now they visualize the similarity between the query points to the input image. So what is the similarity between the blue points to all the other points in B? That's what is being visualized here. And what's being visualized here is the similarity of this background point here to this image. So you can see it highlights nicely kind of like the horse. And here it mostly fires on the, it produced like high similarity on the background as we expect. And this is for another image. So it kind of like shows that the representation is invariant to the texture of the zebra. And it kind of like highlights the patches that are kind of like semantically placed in the same body part, essentially here. Okay. Okay, so I think we're very good with time today, and that gives me an opportunity to also show you one of my work. So if you remember in the beginning of these lectures, I talked about, that I like to think of self-supervised method as divided into these two subgroups, and I mostly talked about this definition and framework of self-supervision method, where we kind of like solve a proxy task and extract features, and the end, the target goal is a supervised task, and we tackle it with transfer learning. But now what I want to show you is I want to show you kind of like a work from this line of self-supervised method that, you have some task, you want to solve it, and you can obtain labels automatically for the given task directly. You don't have a proxy task, you are directly kind of like tackling the task that you have in a hand. So specifically here, oh, the videos are not in sync, but here what we wanted to do is, let me try to see if it will be fixed. Okay. So here what we wanted to do, our task was to predict dense depth map in cases where both the camera and the people in the scene are naturally moving. Are you guys all familiar with depth maps? Do you know what it is? Do I need to define this? No, okay. So just kind of like on a very high level. So a depth map, you can see here that there are dark pixels and light pixels. And the color of each pixel here indicates the distance from the camera. So lighter pixels means that this object is closer to the camera than this, okay? So we want to solve for geometry. We want to know what is the geometry of this scene when both the camera and the people in the scene are moving. Typically the traditional setup is that we know the camera poses. We have two cameras, and we have viewpoints that look on the object at the same time. So we have multiple cameras that look on the same object at the same time, and we can basically use multi-view geometry constraint to compute this 3D location. So you can see here that we shoot a ray that goes through, this is the camera center, and we shoot a ray that goes through this pixel, and we shoot a ray that goes through the corresponding pixel in the other view. And by kind of like looking where these two rays intersect, we can compute the 3D location of this point. But in our case, now where both the camera and the object moves, we cannot do this anymore. These geometric constraints break. So if an object moves and now I shoot a ray, it will fall in some random location in 3D space. And if I'll intersect between them, I will get an error, a point which is incorrect. Is that roughly clear? Okay, cool. So the idea here is let's use a data-driven approach to reason about the depth of moving people in a video. And we actually came up with a very surprising source of training data. So it turns out that somewhere in 2016, there was this viral line of videos in YouTube where people imitate mannequin. So they freeze in some natural pose, and there is a camera moving in space and capturing them. Like you can see here, this one is an extreme example. You can see that everything is frozen, including the people in the audience, and it looks super realistic. I mean, this is a realistic, they unfreeze in the end, but this is kind of like, an example where you can get like an amazing source of training data. So why I'm saying this is an amazing source of training data, because there are many such videos. So people are frozen, camera is moving, and wait, and I want to go back to this slide. So now with these frozen videos, now we are back to this setup. You know, we have multiple views of the same object from different viewpoint, and we can apply geometric constraints to compute their geometry, right? Because they are not moving. So we are no longer in this setup. Now we are in this setup. Okay, so we gathered a large set of those videos, which are very fun to look at also. And we used advanced processing and methodologies from computer vision and geometry estimation to compute pseudo ground truth, to infer the camera poses and to infer the depth maps for those kind of like videos. So now we have, you know, training data. We have images with ground truth depth that we can compute from structure full motion and multi-view stereo algorithms. And we can use this to train a neural network that at test time will be able to operate on videos with moving people and a moving camera. I will not go into all the details about exactly how we do this, but this is generally the setup. What we have here is some network that we train, and the input to that network is an image, along with a mask that indicates where are the people. And we also provided like an initial rough depth map only for the static regions of the scene. So we basically assume that, you know, the people are dynamic, they're moving, the background is mostly static. So we provided with some rough depth map for the environment that we compute from another frame in the video. And this all goes into a deep neural network that predicts a dense depth map. And our loss is basically a loss on a regression loss on the depth map with respect to the pseudo ground truth depth map that we obtain for our training data. Okay? You can see that the training data, you have to do this very carefully. You have to filter out the ground truth very well. You have to reason, you know, about which pixel hairs have high confidence, which one have low confidence. This is a very noisy data and it requires kind of like very careful handling. But in general, once you do this and once you process this training data in kind of like using advanced tools from computer vision and graphics, you can get reliable training data to solve this task. So any questions about the setup?
Yes.
Okay. Yes.
In the case of the ground truth, if we want to predict the ground truth, we will never be better than the ground truth, no?
What? It will, what do you mean by that?
If I want to predict, your target is to predict the ground truth, right?
Yes.
So I assume that the ground truth also has some small errors in the depth or something like that. You will not.
Yes, so that's why you see here that it's not valid everywhere. You see that there are black regions. We actually train this, we applied the loss only on valid pixels, only on like pixels that have like high confidence, that we are kind of like certain that the depth that we get here.
Yes, what I'm asking is, if my result is not good as a ground truth, okay, in the end, why should I use the network and not just use a regular computer vision method?
You don't have this information at test time. At test time, those people are going to be moving, and what you want this network to do is to learn priors about what is the depth of people by training for this task. So you know, people have a consistent size and consistent depth assigned to them. At training time, everything is fixed and we can provide the network with supervision. But at test time, everything, those people are going to be moving, and you cannot use existing MVS techniques to compute their depth because it will be wrong for the moving people. And by training to solve this task, you basically teach the network, given this context of the environment, what should be the depth of those people in the scene, okay?
Tali?
Yes.
So in some sense, like this is you called it a proxy task. Like it is a proxy task because like the differences between the distributions are pretty huge. Here you're training the network to work on these still videos, like still people videos, but you want to work well on a very different distribution where the people are moving.
So I should say that the distribution is not necessary. There is a gap between, we cannot directly input, a video of a moving person here to the network because we don't have this information during training, but it is direct in the sense that we are optimizing our loss is exactly on the output that we want to have for the desired task. It's a depth map. It's not some rotation classification that we then fine tune for depth map. We are solving for the target desired output. There is a gap between, what we can input to that network, but in terms of kind of like this huge gap, I'm not sure it actually exists because these scenes are very natural, diverse. You can see people that in posing in a variety of poses, performing, all sorts of kind of like complicated actions. And this is kind of like a unique case where you have access to such source of data. But my point in showing you this is that, you can sometimes surprisingly and unexpectedly find sources of training data that fits exactly to the task that you want to solve. Okay. And if we take a look on a result, we were able to kind of like significantly outperform all the monocular depth prediction method that existed at that time, and also a stereo method that assumes that the scene is static. So the monocular depth predictions are a method that only takes in an RGB image and predict depth. And this one is looking at a pair of images, but assumes a static scene. And here you can see our result.
So in this method, you do it only per one frame each time, or you give 2 frames?
So we had 2 setups. We had a monocular model that operate only on a single image. But again, I'm going back to this. This is actually a 2 frames model, because this initial depth that we provide to the network is computed from another view of the scene. So you take 2 views, 2 frames in your video. You use, again, like optical flow correspondences to obtain corresponding points. And you use existing techniques to obtain this kind of like, you infer depth for the environment.
Yes, but this is doing training,
what?
Right?
No, this is also done during test time. This is the input. The input is done in both, in the same way in both test and training time. The background will still be kind of like static in both cases, and we can still reason about what is the depth of the environment, even if the people are moving. So that's what we've done here, and this is kind of like computed with respect to another frame in the video.
The training is done end-to-end, so the mask also been done by convolutional network, or it's this is
so this is a good point. I haven't again discussed all the details here. So the human masks are, today you have like pretty advanced method that can give you pretty reliable human masks. So here we just use mask RCNN to obtain this mask. In the monocular setup, you are only going to input this frame and predict the depth map without these 2 inputs. Okay. And we were able to, again, to significantly improve using both our monocular and this 2 frame model.
So the human masks are like off-the-shelf tools, and the background depth is computer vision techniques based on 2 frames.
Exactly.
Okay.
Exactly. Yes. Okay. I guess, as I said, like today we are really good with times, and with that I'd like to conclude the lecture. Next tutorial will be given by Niv. He will cover variational autoencoders, and next class I'll be talking about videos. And I think we can utilize this time if you have any further questions, or you want me to go back to any part of this lecture.